Hello students, welcome to Sri Jayendra's Rank Zone classes. I am your friend and mentor for coming classes with respect to business mathematics and statistics. This is lecture number 2, chapter number 17, Theoretical Distributions. In this lecture, we will continue with the example number 17.8. Now, see example number 17.8. An experiment succeeds thrice as after it fails. If the experiment is repeated 5 times, what is the probability of having no success at all? An experiment succeeds thrice as after it fails. If the experiment is repeated 5 times, what is the probability of having no success at all? First, you have to denote the succeed by P and failure by Q. So, success by P and failure by Q. Okay. So, here succeeds thrice as after it fails. So, success 3 times, thrice means 3 times the failure means Q. P is equal to 3Q. But where Q is equal to 1 minus P, you can put into it this equation 1 minus P. P is equal to 3 minus 3P. So here 4P is equal to 3. So P is equal to 3 by 4. Now you can find out the Q easily. So Q is equal to 1 minus, put the value of P, 3 by 4. 4 minus 3 by 4. 1 by 4. So N is equal to 5, P is equal to 3 by 4 and Q is equal to 1 by 4. Okay. So now here we have the formula f of x is equal to ncx p raised to x q raised to n minus x. Now put the n is equal to 5, p is equal to 3 by 4 and q is equal to 1 by 4 into this. So we will get 5cx 3 by 4 raised to x 1 by 4 raised to 5 minus x, where for n is equal to 0 to 5. So probability of having no success means all failure. So f of 0, no success means f of 0. So we can write 5c0, 3 by 4 is to 0, 1 by 4 is to 5 minus 0. So here we get 5c0, 5 factorial, 0 factorial, 5 minus 0, 5 factorial, raised to 0, 1 into 1 by 4 raised to 5. Cancel 0, 1 by 0 factorial, it is 1. So 1 upon 4 raised to 5. So 1 upon 4 into 4 into 4 into 4 into 4. 4 4s are 16, 16 4s are 64, 64 4s are 256, 256 4s are 1024. So it is 1 upon 1024, 1 upon 1024. Now next example is 17.9. what is the mode of the distribution for which mean and SD are? Mean is given means NP. SD is given root 5. So it is sigma square. SD is equal to sigma square. So square is equal to NPQ and SD is equal to root NPQ. Okay, so here NP is equal to 10 under root NPQ is equal to root 5. Root cancel. So NPQ is equal to 5. Now put the NP is equal to 10 into this. 10 into Q is equal to 5. So Q is equal to 5 by 10. 5 2s are 10. So Q is equal to 1 by 2. For P, 1 minus Q. 1 minus 1 by 2. It is 1 by 2. So N is equal to 20. We will get from the P and Q. Put the value of P and Q into this. So here NP is equal to 10. So N 1 by 2 is equal to 10. So you will get N is equal to 10 to the 20. N is equal to 20. Hence mode is equal to largest integer contained in N plus 1 into P is equal to largest integer contained in 20 plus 1 into 1 by 2. Largest integer contained in 21 by divided by 2 is equal to 10.50. So it is largest integer contained in 10.50 is 10. So the answer is 10. Okay. Now move to the example 17.10. If x and y are two independent binomial variables with parameters 6 and 1 by 2 and 4 and 1 by 2 respectively. What is probability of x plus y greater than or equal to 1? X and y both are independent binomial variables with parameters 6 and 1 by 2 and 4 and 1 by 2. Okay. Here z is equal to x plus y. It follows that z also allows binomial distribution with parameters. So 6 plus 4 and 1 by 2. So 10 and 1 by 2. Hence here probability of x plus y greater than or equal to 1. Instead of x plus y, write down the z. So here p of z greater than or equal to 1. Okay. So you can write 1 minus p of z less than 1. So here z less than 1 means only z is equal to 0. So 1 minus nc0, 10c0, probability 1 by 2 raised to 0, 1 by 2, 10 minus 0. 1 minus 1 into 1, 1 by 2 raised to 10. So 1 minus 1 upon 2 raised to 10. So 1 minus 1 upon 1, 0, 2, 4. 1, 0, 2, 4 minus 1 upon 1, 0, 2, 4 is equal to 1, 0, 2, 3 upon 1, 0, 2, 4. One zero two three upon 1, 0, 24. Now, next topic is Poisson distribution. Poisson distribution. Previously we have discussed about the binomial distribution, and now we will discuss about the Poisson distribution. Poisson distribution is a theoretical discrete probability distribution which can describe many processes. Simon Denis Poisson of France introduced this distribution way back in the year 1837. Now, Poisson model. Let us think of a random experiment under the following conditions. First, the probability of finding success in a very small time interval t, t plus dt is kt, where k greater than 0 is a constant. Second, the probability of having more than one success in this time interval is very low. Third one is the probability of having success in this time interval is independent of t as well as earlier successes. The above model is known as Poisson model. The probability of getting x successes in a relatively long time interval t containing m small time intervals, so it is intervals t, small t, so t is equal to m t, is given by e raised to minus kt into kt raised to x divided by x factorial for x is equal to 0, 1 to infinite, up to infinite. Taking kt is equal to m, the above form is reduced to e raised to minus m into m raised to x upon x factorial for x is equal to 0, 1 to infinite. Definition of Poisson distribution. A random variable x is defined to follow Poisson distribution with parameter lambda to be denoted by variable x probability of m. The probability of mass function of x is given by f of x is equal to p of x is equal to x e raised to minus m into m raised to x upon x factorial for x is equal to 0, 1 to infinite, is equal to 0 otherwise. Okay. Previously, binomial distribution formula is f of x is equal to ncx p raised to x q raised to n minus x, and Poisson distribution formula is e raised to minus m into m raised to x upon x factorial. Here E is a transcendental quantity with an approximate value as 2.71828. E is equal to 2.71828. It is wiser to remember the following important points in connection with Poisson distribution. First, since e raised to minus m is equal to 1 upon e raised to m greater than 0, whatever may be the value of m greater than 0, it follows that f of x greater than or equal to 0 for every x. Also, it can be established that sum of x, f of x is equal to 1. So, f of 0 plus f of 1 plus f of 2 plus up to f of infinite is equal to 1. Second is Poisson distribution is known as uniparametric distribution as it is characterized by only one parameter m. Third one is the mean of Poisson distribution is given by m, mu is equal to m. The variance of Poisson distribution is given by sigma square is equal to m. Like binomial distribution, Poisson distribution could be also unimodal or bimodal depending upon the value of the parameter m. Vmu0 is equal to the largest integer contained in m if m is a non-integer. Mu0 is equal to m and m minus 1 if m is an integer. Next is Poisson approximation to binomial distribution. If n the number of independent trials of a binomial distribution tends to infinity and p, the probability of a success tends to 0 so that m is equal to np remains finite. Then a binomial distribution with parameters n and p can be approximated by a Poisson distribution with parameter m is equal to np. In other words, when n is rather large and p is rather small, so that m is equal to np is moderate, then beta of np equivalent to probability of m, or you can say that binomial distribution of np equivalent to Poisson's distribution. Okay. Additive property of Poisson distribution. If x and y are two independent variables following Poisson distribution with parameters m1 and m2, z is equal to x plus y also follows Poisson distribution with parameter m1 plus m2. If x is variable of Poisson distribution of m1, y for p of m2, x and y are independent, then z is equal to x plus y. It is p of m1 plus m2. Now, next is application of Poisson distribution. Poisson distribution is applied when the total number of events is pretty large, but the probability of occurrence is very small. Thus, we can apply Poisson distribution rather profitably for the following cases of A. The distribution of the number of printing mistakes per page of a large book. The distribution of the number of printing mistakes per page of a large book. B is the distribution of the number of road accidents on a busy road per minute. C. The distribution of the number of radioactive elements per minute in a fusion process. D. The distribution of the number of demands per minute for health center and so on. Now, example 17.11. Find the mean and standard deviation of x where x is Poisson variate satisfying the condition P of x is equal to 2 is equal to P of x is equal to 3. In the question, first you have to read question carefully, okay. Here given that Poisson variate satisfying, okay. So here we have to use the Poisson formula, okay. So let x be a Poisson variate with parameter m. The probability max function of x is then given by f of x is equal to e raised to minus m into m raised to x upon x factorial for x is equal to 0, 1 to infinite. Now P of x is equal to 2 is equal to P of x is equal to 3. So you can write f of 2 is equal to f of 3. F of 2 is equal to e raised to minus m into m square upon 2 factorial. F of 3 is equal to e raised to minus m into m cube upon 3 factorial. So here e raised to minus m square 2 factorial e raised to minus m cube 3 factorial. E raised to minus m cancel, square 1m here. So 3 factorial upon 2 factorial is equal to m. So m is equal to 3 into 2 factorial m is equal to 3. Thus the mean of this distribution is m is equal to 3 and standard deviation is root m approximate to 1.73. Example 17.12. The probability that a random variable x following Poisson distribution would assume a positive value is 1 minus e raised to minus 2.7. What is the mode of the distribution? Now solution is, if the probability mass function is given by f of x is equal to e raised to minus m into m raised to e raised to minus m into m raised to x upon x factorial for x is equal to 0, 1, 2 up to infinite. The probability that x assume a positive value p of x greater than 0. So 1 minus probability of x less than or equal to 0. So here we can write 1 minus probability of x is equal to 0. So 1 minus f of 0. So f of 0 is equal to e raised to minus m into m raised to 0 upon 0 factorial is equal to e raised to minus m. Here x, okay, not 2. So 1 minus e raised to minus m. So m, value of m compared with 1 minus e raised to minus m compared with 1 minus e raised to minus 2.7. 1 cancel, e raised to minus m, e raised to 2.7 minus 2.7. So you can write minus m is equal to minus 2.7, minus minus cut, so it is m is equal to 2.7. Thus mu 0 is equal to largest integer contained in 2.7. So largest integer is 2. Now example 17.13. The standard deviation of a Poisson variate is 1.732. What is the probability that the variate lies between minus 2.3 to 3.68? Let x be a Poisson variate with parameter m. Then SD of x is root m. As given, root m is equal to 1.732. So here m is equal to, take this square of 1.732. So it is approximately 3. The probability that x lies between minus 2.3 and 3.68. So minus 2.3 less than x less than 3.68. So it is f of 0 plus f of 1 plus f of 2 plus f of 3. So f of 0, it means e raised to minus 3 into 3 raised to 0 upon 0 factorial plus e raised to minus 3 into 3 raised to 1 upon 1 factorial plus e raised to minus 3 into 3 square by 2 factorial plus e raised to minus 3 into 3 cube by 3 factorial. So e raised to minus 3 into 1 plus e raised to minus 3 into 3 plus e raised to minus 3 into 9 by 2 plus e raised to minus 3 27 by 3 into 2 into 1, 3 nines. So e raised to minus 3 common, 1 plus 3 plus 9 by 2 plus 9 by 9 by 2. So e raised to minus 3, 2, 9 plus 9 by 2. So e raised to minus 3, 6 plus 2, 8, 9 plus 9, 18 plus 86, 26 by 2. So it is 13 e raised to minus 3. You can write as 13 by e raised to 3. Now put the value of e, as e is equal to 2.71828. So 2.71828 cube. Using Kelsey, you can find out the approximate value is 0.65. 0.65. Okay. Now next is example 17.14. X is a Poisson variate satisfying the following relation. P of x is equal to 2 is equal to 9. P of x is equal to 4 plus 90. P of x is equal to 6. What is the standard deviation of x? Here we have to find out the standard deviation of x. Let x be a Poisson variate with parameter m. Then the probability mass function of x is P of x is equal to x is equal to f of x is equal to e raised to minus m into m raised to x upon x factorial for x is equal to 0, 1 to infinite. Thus P of x is equal to 2. So you can write f of 2 is equal to 9 f of 4 plus 90 f of 6. So here first you have to find out the f of 2. e raised to minus m square upon 2 factorial. F of 4, it means e raised to minus m raised to 4 upon 4 factorial. F of 6, it means e raised to minus m into m raised to 6 upon 6 factorial. Now, put the value of f of 2, f of 4 and f of 6 into this. So, e raised to minus m both side cancel. So, m square by 2 common 90m raised to 4 upon 360 plus 9m square by 12 minus 1 is equal to 0. So, here 90 4s are 3 3s are 9, 3 4s are 12. So, it is e raised to minus m into m square 4, 2 4s are 8, m raised to 4 by 4 plus 3m square by 4 minus 1 is equal to 0. So, e raised to minus m into m square plus 4 into m square minus 1 is equal to 0. So, here m square plus 4 not equal to 0. E raised to minus m greater than 0. So, here m square minus 1, it means m minus 1, m plus 1 is equal to 0. So, m is equal to 1, m is equal to minus 1. So, not consider m is equal to 1. Thus, the standard deviation of x is under root 1 is equal to 1. Now, move to the example 17.15. Between 9 and 10 am, the average number of phone calls per minute coming into the switch mode of a company is 4. Find the probability that during one particular minute there will be first, no phone calls. Second, at most 3 phone calls given e raised to minus 4 equal to 0.018316. Now solution. Let x be the number of phone calls per minute coming into the switchboard of the company. We assume that x follows Poisson distribution with parameters m is equal to average number of phone calls per minute is equal to 4. The probability that there will be no phone call during a particular minute. So, probability of x is equal to 0. So, is equal to e raised to minus 4 into 4 raised to 0 by 0 factorial is equal to e raised to minus 4 into 1 upon 1 is equal to e raised to minus 4. Value of e raised to minus 4 is 0.018316. Now, question 2 is the probability that there will be at most 3 phone calls. At most 3 phone calls. Most maximum 3. Minimum any. So probability x less than or equal to 3. So probability x is equal to 0 plus probability x is equal to 1. Probability x is equal to 2. Probability plus probability x is equal to 3. So here e raised to minus 4 into 4 raised to 0 by 0 factorial plus e raised to minus 4 into 4 raised to 1 by 1 factorial plus e raised to minus 4 into 4 square by 2 factorial plus e raised to minus 4 into 4 cube by 3 factorial. E raised to minus 4 common, 1 plus 4 plus 16 by 2, 2 8 plus 64 by 6. 2 3 232. So here 1 plus 4 plus 8 plus 32 by 3. 13 plus 32 by 3. 39 plus 32 plus 39 plus 32 is 71 divided by 3. So e raised to minus 4 into 71 by 3, 0.018316 into 71 by 3 is approximately 0.43. Example 17.16. If 2% of electric bulbs manufactured by a company are known to be defectives, what is the probability that a sample of 150 electric bulbs taken from the production process of that company would contain, first, exactly one defective bulb, second, more than 2 defective bulbs? Now the solution is let X be the number of bulbs produced by the company. Since the bulbs could be either defective or non-defective and the probability of bulb being defective remains the same, it follows that X is a binomial. Variate with parameters n is equal to 150 and p is equal to probability of a bulb being defective is equal to 0.02. However, since n is large and p is very small, we can approximate this binomial distribution with Poisson distribution with parameter m is equal to np is equal to 150 into 0.02 is equal to 150 into 0.02 is equal to 3. So first one is the probability that exactly one bulb would be defective. Probability of X is equal to 1. E raised to minus 3 into 3 raised to 1 upon 1 factorial. E raised to minus 3, 3 into 2 into 1 upon 1 is equal to here e raised to minus 3, 3 raised to 1 upon 1 factorial. So, e raised to minus 3 into 3 upon 1 is equal to 3 by e cube. 3 by e cube. So 3 by 2.71828 raised to cube. Using Kelsey, we can solve these. Okay. Approximate value is 0.15. Now 2 is the probability that there would be more than 2 defective bulbs. More than 2. It means first probability of more than 2, probability of x greater than 2. But here we can also write as 1 minus p of x less than or equal to 2. That is the probability of x greater than 2. Okay. So 1 minus f of 0 plus f of 1 plus f of 2. So 1 minus e raised to minus 3 into 3 is raised to 0 by 0 factorial plus e raised to minus 3 into 3 raised to 1 by 1 factorial plus e raised to minus 3 into 3 square by 2 factorial. So 1 minus 8.5 into e raised to minus 3, 1 minus 0.4232, so 0.5768 equivalent to 0.58. Now next is 17.17. The manufacturer of a certain electronic component is certain that 2% of his product is defective. He sells the component in boxes of 120 and guarantees that not more than 2% in any box will be defective. So find the probability that a box selected at random would fail to meet the guarantee. Given that e raised to minus 2.40 equivalent to 0.0907. Now solution is, let x denote the number of electric components, then x follows binomial distribution with n is equal to 120 and p is equal to probability of a component being defective is equal to 0.02. As before, since n is quite large and p is rather small, we approximate the binomial distribution with parameters n and p by a Poisson distribution with parameters m is equal to np. So it is 120 into 0.02 is equal to 2.40. Probability that a box selected at random would fail to meet this specification is equal to probability that a sample of 120 items would contain more than 2.40 defective items. P of x greater than 2.40, 1 minus p of x less than or equal to 2.40. So 1 minus p of x is equal to 0 plus p of x is equal to 1 plus p of x is equal to 2. So 1 minus e raised to minus 2.40 plus e raised to minus 2.40 into 2.4 plus e raised to minus 2.40 into 2.40 divided by 2 square. So 1 minus e raised to minus 2.40 in the bracket 1 plus 2.40 plus 2.40 square by 2. So after solving, 1 minus 0.0907 into 6.28, we will get the approximate value is 0.43. Now next example 17.18. A discrete random variable x follows Poisson distribution. Find the value of p x is equal to at least 1. Second one is p x less than or equal to 2 divided by x greater than or equal to 1. you are given e of x is equal to 2.20, e raised to minus 2.20 is equal to 0.1108. Since x follows Poisson distribution, it is probability mass function is given by f of x is equal to e raised to minus m into m raised to x upon x factorial for x is equal to 0, 1 to infinite. Now P first is P x is equal to at least 1, at least 1. So maximum anything, least 1, minimum 1. So 1 minus P of x less than 1. 1 minus P of x is equal to 0. 1 minus e raised to minus m. Put the value of m 2.20. 1 minus e raised to minus 2.20 is equal to 1 minus 0.1108 approximate value is 0.89. 0.89. For 2, P of x less than or equal to 2 divided by x greater than or equal to 1. P of x less than or equal to 2 intersect with x less than or equal to 1 divided by P of x less than or equal to P of x greater than or equal to 1. So P of x is equal to 1 plus P of x is equal to 2 upon 1 minus P of x less than 1. So f of 1 plus f of 2 upon 1 minus f of 0. So f of 1 plus f of 2 e raised to minus m into m plus e raised to minus m into m square by 2 upon 1 minus e raised to minus m. Into m square by 2 upon 1 minus e raised to minus m. E raised to minus m common, 1 plus m by 2, 1 minus e raised to minus m. So here e raised to minus 2.20 into 2.2 plus e raised to minus 2.20 into 2.20 square by 2. So after solving this by 0.5119 divided by 0.8892, approximate value is 0.58. Fitting a Poisson distribution. As explained earlier, we can apply the method of moments to fit a Poisson distribution to an observed frequency distribution. Since Poisson distribution is uniparametric, we equate m, the parameter of Poisson distribution, to the arithmetic mean of the observed distribution and get the estimate of m. M is equal to x bar. The fitted Poisson distribution is then given by f of x is equal to e raised to minus m into m raised to x upon x factorial. Now, example 17.19. Fit a Poisson distribution to the following data: number of death, frequency, number of death 0, 1, 2, 3, 4, frequency 122, 46, 23, 8, 1. The mean of the observed frequency distribution is x bar is equal to sum of f I x I upon capital N, where N is equal to sum of f, is equal to minus 122 into 0 plus 46 into 1 plus 23 into 2 plus 8 into 3 plus 1 into 4 upon 122 plus 46 plus 23 plus 8 plus 1. So 1200 divided by 200, 120 divided by 200, so 006. So 0.6 by 10 is equal to 0.6. Thus m at is equal to 0.6, hence f at 0 is equal to e raised to minus m, e raised to minus 0.6 is equal to 0.5488. So f at of 1 is equal to e raised to minus m into m upon 1 factorial. So 0.6 into e raised to minus 0.6 is equal to 0.3293. 0.6 square upon 2 factorial into 0.5488 is equal to 0.0988. So 0.6 cube by 3 factorial into 0.5488 is equal to 0.0198. Lastly, p of x greater than or equal to 4. 1 minus p of x less than 4. Fitting Poisson distribution to an observed frequency distribution of deaths. X is equal to 0, 1, 2, 3, 4 or more total. F of x 0.5488. For f of 1 it is 0.3293. F of 2 0.0988. For f of 3 0.0198. For more 4 or more total 0.0033 by subtraction, and total is 1. N into f of x 109.76 is equal to 110, 65.86 65, 19.76 20, 3.96 is equal to 4, 0.661, total 200. So observed frequency 122, 46, 23, 8, 1. 200. New topic: normal or Gaussian distribution. The two distributions discussed so far, namely binomial and Poisson, are applicable when the random variable is discrete. In case of continuous random variable like neighbor or variable like height or weight, it is impossible to distribute the total probability among different mass points, because between any two unequal values there remains an infinite number of values. Thus, a continuous random variable is defined in terms of its probability density function f of x, provided, of course, such a function really exists. F of x satisfies the following condition: f of x greater than or equal to 0 for x belongs to minus infinite to infinite, and minus infinite to infinite f of x is equal to 1. Limit integration of minus infinite to plus infinite f of x is equal to 1. The most important and universally accepted continuous probability distribution is known as normal distribution. So, many mathematicians like De Morgan, Laplace, etc. contribute towards the development of normal distribution. Carl Gauss was instrumental for deriving normal distribution, and as such normal distribution is also referred to as Gaussian distribution. A continuous random variable x is defined to follow normal distribution with parameters mu and sigma square to be denoted by x n function of mu sigma square. So, if the probability density function of the random variable x is given by f of x is equal to 1 upon sigma under root of 2 pi e raised to minus x bar minus u square divided by 2 sigma square for minus infinite to x to plus infinite, where mu and sigma are constant and sigma greater than 0. Some important points relating to normal distributions are listed below. The name normal distribution has its origin some 200 years back as mathematicians were in search for a normal model that can describe the probability distribution of most of the continuous random variables. If we plot the probability function y is equal to f of x, then the curve known as probability curve takes the following shape. Showing normal probability curve. A quick look at figure 17.1 reveals that the normal curve is bell shaped and has one peak, which implies that the normal distribution has one unique mode. The line drawn through x is equal to mu has divided the normal curve into two parts, which are equal in all respects. Such a curve is known as symmetrical curve and the corresponding distribution is known as symmetrical distribution. Thus, we find that the normal distribution is symmetrical about x is equal to mu. It may also be noted that the binomial distribution is also symmetrical about p is equal to 0.5. We next note that the two tails of the normal curve extend identically on both sides of the curve. The total area of the normal curve or for that any probability curve is taken to be unity, one since the vertical line drawn through x is equal to mu. Divide the curve into two equal halves, it automatically follows that the area between minus infinite to mu, the area between mu to infinite is equal to 0.5. When the mean is 0, we have the area between minus infinite to 0 is equal to the area between 0 to infinite is equal to 0.5. See, if we take mu is equal to 0 and sigma is equal to 1, we have f of x is equal to 1 upon under root 2 pi e raised to minus z square by 2 for minus infinite to less than z less than 8. The random variable z is known as standard normal variable or standard normal deviate. The probability that a standard normal variate x would take a value less than or equal to a particular value, say x is equal to small x, is given by phi of x is equal to p of x less than or equal to x. Phi of x is known as the cumulative distribution function. We also have phi of 0 is equal to p of x less than or equal to 0. Area of the standard normal curve between minus infinite and 0 is equal to 0.5. D. The normal distribution is known as biparametric distribution as it is characterized by two parameters, mu and sigma square. Once the two parameters are known, the normal distribution is completely specified. Properties of normal distribution. Pi is equal to 22 by 7 e raised to minus theta is equal to 1 by e raised to theta greater than 0. F of x greater than or equal to 0 for every x, it can be shown that minus infinite to infinite f of x dx is equal to 1. The mean of the normal distribution is given by mu. Further, since the distribution is symmetrical about x is equal to mu, it follows that the mean, median and mode of normal distribution coincide, all being equal to mu. The standard deviation of the normal distribution is given by sigma. Mean deviation of normal distribution is sigma root 2, approximate 0.8 sigma. The first and third quartiles are given by q1 is equal to mu minus 0.675 sigma. q3 is equal to mu plus 0.675 sigma. So that quartile deviation 0.675 sigma the normal distribution is symmetrical about x is equal to mu. As such, its skewness is 0. The normal curve is neither inclined move toward the right nor towards the left, positively skewed. The normal curve y is equal to f of x has 2 points of inflection to be given by x is equal to mu minus sigma and x is equal to mu plus sigma. At these 2 points, the normal curve changes its curvature from concave to convex and from convex to concave. If x to n mu sigma square, then z is equal to x minus mu upon sigma minus n upon 0,1 is known as standardized normal variate or normal deviate. We also have pz less than or equal to k is equal to phi of k. The value of phi of k for different k are given in a table known as Biometrica. Because of symmetry, we have phi of minus k is equal to 1 minus phi of k. We can evaluate the different probabilities in the following manner. P of x less than a is equal to p of x minus mu upon sigma less than a minus mu upon sigma. Probability is p of z less than k, k is equal to a minus mu upon sigma is equal to phi of k. Also p x less than or equal to a p of x less than a as x is continuous, p of x greater than b is equal to 1 minus p x less than or equal to b. So 1 minus 5 b minus mu upon sigma. So p of a less than x less than b is equal to 5 b minus mu upon sigma minus 5 a minus mu upon sigma. Ordinate at x is equal to a is given by 1 upon sigma phi into a minus mu upon sigma also phi into minus k is equal to phi of the value of phi of k for different k are also provided in the biometrica table. Area under the normal curve is shown in the following figure. Mu minus 3 sigma, mu is equal to minus 3 mu minus 2 mu minus 3 sigma upon z is equal to minus 3, minus 2, minus 1, 0, 1, 2 and 3. So plot onto the graph. Here mu minus 3 sigma, mu minus 2 sigma, mu minus sigma x is equal to mu plus sigma, mu plus 2 sigma, mu plus 3 sigma. All the values represented here in this diagram. So that is the diagram of area under normal curve. From this figure we find that P of mu minus sigma less than x less than mu is equal to P in the bracket mu less than x less than mu plus sigma is equal to 0.34135, or alternatively P minus 1 less than z less than 0 is equal to P into 0 less than z less than 1 is equal to 0.34135. P mu minus 2 sigma less than x less than mu is equal to P mu less than x less than mu plus 2 sigma is equal to 0.47725. So P minus 2 less than less than 1 is equal to P of 1 less than z less than 2, 0.47725. P of minus P of mu minus 3 sigma less than x less than mu is equal to P of mu less than x less than mu plus 3 sigma is equal to 0.49865. P of minus 3 less than z less than 0 is equal to P zero less than z less than 3 is equal to 0.49865. Combining this result, we have P of mu minus sigma less than x less than mu plus sigma is equal to 0.6828. P minus 1 less than x less than 1 is equal to 0.6828. P of mu minus 2 sigma less than x less than mu plus 2 sigma is equal to 0.9546. P of minus 2 less than P of minus 2 less than z less than 2 is equal to 0.9546. P of mu minus 3 sigma less than x less than mu plus 3 sigma is equal to 0.9973. P of minus 3 less than 3, 0.9973. We note that 99.73% of the values of a normal variable lies between mu minus 3 sigma and mu plus 3 sigma. Thus, the probability that the value of x lies outside that limit is as follows, as low as 0.0027. If x and y are independent normal variable with means and standard deviation as mu1 and mu2 and sigma 1 and sigma 2 respectively, then z is equal to x plus y also follows normal distribution with mean mu1 plus mu2 and sd is equal to under root of sigma 1 square plus sigma 2 square respectively. If x to n mu1 sigma 1 square, for y mu2 sigma 2 square, and x and y are independent, then z is equal to x plus y minus n mu1 plus mu2 plus sigma 1 square plus sigma 2 square. Now this lecture is over here. Next time we will start with the applications of normal distribution. So see you soon. Bye.